The last couple of video lectures have been focused on the process of using Gaussian elimination to find a solution or a family of solutions to a system of equations. In this video, I want to think about systems of equations a bit more abstractly, and I want to discuss different perspectives, what are sometimes called the row perspective and the column perspective, how we should think about solving a system of equations and what that solution means. The approach we've taken so far has treated each row separately. This is the row perspective. In one of the examples that I worked out in a video, we looked at a particular system of equations that I have written here and highlighted in green, purple, and yellow. Each one of these equations represents a plane in 3 dimensions, and we found a unique solution to this system. It turned out that the solution was -1, 2, and 2. And you can think of that as being the point at which these 3 planes intersect. There's a green plane and a purple plane and a yellow plane. The purple plane and the green plane intersect in a line, and then the green plane and the yellow plane intersect in a line, and the line of intersection intersects the yellow plane in a point. So when we're looking for the solution, we're looking for that unique point that solves, well, in this case it was a unique point, but the unique point that solves all of these equations simultaneously. This is a lot different than the column perspective. So what do I mean by the column perspective? I don't mean we're going to be thinking about the columns as giving us planes, but rather that the solution to the system of equations is telling us exactly the right linear combination of column vectors that satisfy a particular vector equation. When we have our system of equations, if we extract all of the coefficients in front of the x's, that becomes the column vector 1, 4, -2 in this example. If we extract the coefficients that are in front of the y's, the 2, 9, and -3 becomes another column vector. And likewise, -1, -3, 7 is another column vector. When we seek a solution, in this case that solution was -1, 2, 2, what we're trying to find are the values of x, y, and z that work out to where we would produce the column vector 1, 8, 10. What we're looking at here is called a vector equation. We're looking at a linear combination of vectors, a scalar multiple times the first column vector, plus a scalar multiple times the second vector, and a scalar multiple times the third vector. That linear combination then gives us the column vector 1, 8, 10. X and y and z, these are the scalars in this vector equation. And our solution is, what are the scalars that we need to find? So in other words, the solution is how much you need to scale these 3 vectors in such a way that you can add them together and then get 1, 8, 10. For this particular solution, we needed to scale x by -1, and we needed to scale y and z up by 2. There's a pictorial way to think about this. If we're trying to figure out how much we need to scale these 3 vectors so they add up into a 4th vector, what we're asking is, well, how much do I need to scale my first column vector v1 and my second column vector v2 and my third column vector v3, so that the last column vector, which is the one that we usually call b, can be realized as the diagonal of the parallelepiped that's spanned by the 3 column vectors v1, v2, and v3. So the column perspective is really quite different from the row perspective. We're trying to find the right linear combination. We're trying to find the scalars c1, c2, and c3 that solve a particular vector equation, cv1 plus c2v2 plus c3v3 equal to some vector b. And it's that c1, c2, c3, these 3 scalars, that give us the solution, x, y, and z. What I'd like to do now is work through a concrete, simple example and think about the row perspective and the column perspective as we work through this example. So let's make a little space on our page and start doing the following example. We're going to be looking at the vector equation where we're trying to add together column vectors 1, 3 and -2, 1 and to get -4, 9. And we're seeking x and y. These are the scalars that would give us a solution to this vector equation. So notice that this is a repackaging of what we're used to looking at This vector equation is the same thing as the system of equations x minus 2y equals minus 4 and 3x plus y equals 9. So these are two lines in two-dimensional Euclidean space, and we're going to be looking to figure out whether they intersect, and if they do, where is the point where they intersect. So let's go ahead and solve it with the row perspective, the way we have solved it before using Gaussian elimination. So for our row perspective solution, we're going to form an augmented matrix. That augmented matrix will look like 1, 3, minus 2, 1, and then a dotted line to separate the coefficients from the vector that we usually call b. And we're going to apply a series of row operations to put it into reduced row echelon form. So my first row operation is going to be minus 3 row 1 plus row 2 to replace row 2. Because I like to use my down and to the right strategy. That's going to clear out the 3 that appears in the first entry of the second row. I do that, and I have 1, minus 2, minus 4 in the first row, and I get a 0, 7, 21 in the second row. I'm going to follow this up with the row operation that divides the second row by 7. So 1 over 7, row 2, so that I'm looking at the second row being just 0, 1, 3. And then here, I'm in row echelon form, but not reduced row echelon form. I do have the stair step showing up, but now I want to take the rightmost pivot, which is a 1, and use it to eliminate the 2. So the last row operation that I'm going to apply is 2 row 2 plus row 1, and that's going to go into row 1. That's going to produce for me a 1, 0, and a 2 in the first row. And then I have my 0, 1, 3 unchanged. So with my row perspective, what I do is I use my method of Gaussian elimination to reduce the matrix and then read off the solution, which is easy to see now as y equals 3 and x equals 2. This is the point at which the two lines, x minus 2y equals minus 4 and 3x plus y equals 9, intersect in a single point. Let's go ahead and check that this works. We're going to check it in two different ways. So let's check our answer. First, I want to check that it solves the system of equations. So I have, let's see, x equals 2 and y equals 3. That was my solution. So I want to check my two equations. I have 2 minus 2 times 3. That does equal minus 4. And I have 3 times 2 plus 3, and that works out to be 9. So it does solve both of the equations. So that's good. But we can also check it as a vector equation as well. This is also going to work, of course. But what we want to see is that the vector equation, that's the column perspective, is going to be solved by this value of x and y as well. And indeed, if I take my vector equation where I'm trying to find the right scalar, so that if I add 1, 3 and minus 2, 1 together to get minus 4, 9, then taking x to be 2 and y to be 3 gives me the two column vectors 2, 6, minus 6, 1, which do add up to give me minus 4, 9. So it checks out as a vector equation as well. From here, I can also see the column perspective. When I look at this vector equation, it tells me that I need to scale x up by 2, and I need to scale y up by 3. And if I do so and add them together, then I'm going to produce this vector minus 4, 9, which from the pictorial discussion before is going to be seen as the diagonal of the parallelogram that's spanned by my column vectors. So let's see what that looks like. Here is the sketch of the solution. My two vectors, 1, 3 and minus 2, 1, are pictured here as the small vectors in green and in purple. Oops, in purple. My solution tells me that I need to scale green up and that I also need to scale purple up by 3. That gives me the longer versions of the green vector and the purple vector. When I do vector addition and I add them together, tip to tail, either in this direction or in this direction, the vector that comes out as their sum is the diagonal of the parallelogram. This is the vector b, which is -4, 9. There's yet one more way to think of this, not just as the row perspective and the column perspective, but we can also think of this in terms of a matrix equation as well, which is something we're going to be exploring a lot more in the next few lectures. But here is another way to package this exact same system of equations. Here, we're going to consolidate the 2 column vectors in a matrix. The 1, 3, the first column vector, just becomes the first column of this matrix, and the second column vector becomes the second column of this matrix. But where do I put the scalars x and y? Well, I'm going to write them as a column vector, and I'm going to think about a matrix times a vector as producing another vector. Don't worry, this is something I'm going to be talking a lot more about, but this is another way to think of a system of equations. And we'll be exploring that more very soon.